I want you to close your eyes and try to picture absolutely nothing. Not a dark room and not the empty space between stars. An absolute, total void. No time, no dimensions, and no light to cast a shadow. It is a concept the human brain isn't wired to process. Yet the smartest people in the room, using our most advanced math, believe that every single thing in our reality, from the device you're watching to the Andromeda Galaxy, burst out of that state of absolute zero. It's the ultimate free lunch. To figure out how you get a universe from non-existence, we have to bridge two radically different scales. We have to take cosmology, the study of the largest event in history, and smash it into particle physics, the study of the tiniest objects ever recorded. 13.8 billion years ago, the entire universe was squeezed into a space smaller than a subatomic particle. At that scale, the rules of the tiny governed everything. To understand the explosion, we have to look closely at the shrapnel it left behind. Let's open the pantry and look at the actual ingredients of the universe. What we experience as solid matter is mostly empty space. Even the protons and neutrons inside an atom aren't solid marbles. They are bags containing even smaller, more fundamental building blocks called fermions, specifically a type of fermion with a whimsical name, quarks. You will never find a quark alone. They are bound together by the strong nuclear force. If you try to pull two quarks apart, it is like stretching a rubber band. When the band snaps, the raw energy immediately turns into mass, creating a new pair of quarks. Matter refuses isolation. Alongside quarks are leptons, including the ghostly neutrino, which ignores almost everything in its path. Trillions of them from the sun are streaming through your body right now, as if you were just a vacuum. You have a pile of these subatomic bricks, but they won't build reality without mortar. That is where the bosons come in. They are the force carriers. When two magnets repel each other, they are literally throwing streams of messenger particles at each other to communicate the force. Reality is a dynamic framework of interacting particles and forces. If you remove all of them to create a perfect void, you uncover the mechanism that started the universe. In modern physics, nothing is almost never empty. A pure quantum vacuum is a restless, seething cauldron of activity. This stems from the Heisenberg uncertainty principle. One version of this mathematical law dictates that for incredibly short fractions of a second, the energy level of empty space can fluctuate wildly. Empty space can borrow energy from the future to create mass, popping a virtual particle and its antiparticle twin into existence out of thin air. Nature allows this million-dollar loan, provided the two particles instantly crash back together, annihilate each other, and return the balance to zero. This is happening everywhere, constantly. But if this cosmic debt is always instantly repaid with mutual destruction, how did we get a permanent universe? To get a universe that lasts, you need a physical mechanism capable of ripping those borrowed particles apart so fast that they lose track of each other before they have the chance to cancel each other out. The Big Bang represents the sudden, spontaneous expansion of space itself from a single point of infinite density. A tiny fraction of a second after time zero, the universe underwent cosmic inflation. Space itself stretched outward faster than the speed of light. Einstein proved that nothing can travel through space faster than light, but space itself can expand at any speed it wants. This hyper-expansion solved the quantum loan problem. The virtual particles bubbling in the vacuum were violently ripped to opposite sides of reality. With their partners gone, they couldn't annihilate. The loan was forgiven, and those temporary particles were locked into permanent existence. Following this burst, the universe was a chaotic plasma of loose quarks. As space expanded, it cooled in a process called symmetry breaking. The intense energy dropped just enough for the strong nuclear force to finally clamp down, snapping those quarks together into the universe's first protons. Inflation allowed the universe to take a temporary microscopic quantum fluctuation and freeze it in place, generating the permanent reality we inhabit today. For the first 380,000 years, the universe was a searingly hot, completely opaque fog. Free-roaming electrons were buzzing around with so much energy that light could not travel more than a tiny distance without violently scattering off of them. Then, the universe reached a critical threshold. It cooled to about 3,000 degrees Kelvin, which was just cold enough for protons to pull those chaotic electrons into stable orbits. The first neutral atoms formed, the fog lifted, and light finally traveled freely. In 1965, two scientists testing a radio antenna in New Jersey picked up a persistent hiss. Blaming nesting pigeons, they scrubbed the machine, but the hiss remained. They had accidentally recorded the cosmic microwave background, ancient light matching the Big Bang, showing microscopic seeds of galaxies. This background radiation is the literal, observable echo of the universe's creation, and it is still raining down on Earth right now. Everything we've tracked so far, the quarks, the atoms, the gas clouds, and the stars, makes up a grand total of 5% of the universe. The other 95% belongs to the dark sector. We have dark matter, the invisible glue holding galaxies together, and dark energy, the mysterious force causing the expansion of the universe to accelerate. Our 5% of normal matter was lucky. The early universe produced almost equal amounts of matter and antimatter, which should have completely wiped each other out. But there was a tiny imbalance, just one extra particle of matter for every billion pairs of antimatter. We are the survivors of that great annihilation. Mapping these origins requires a colossal infrastructure, machines the size of cities that generate petabytes of raw information. In 1989, researchers at CERN realized that sharing these massive datasets with thousands of scientists across the globe was physically impossible through traditional means. To solve this, Tim Berners-Lee developed the protocol that became the World Wide Web. Our entire information age is a byproduct of hunting for quarks. The Big Bang exists as a continuous state of being. The quantum mechanism that ignited the universe remains active in the empty air right in front of your face. Standing outside late at night, when the neighborhood is quiet, the Milky Way becomes visible. It hits you with that classic pale blue dot feeling, the humbling realization that you are on a tiny rock orbiting an average yellow star, and all your daily problems are entirely insignificant. We naturally find comfort in that view. The night sky feels peaceful. Images from space telescopes like Hubble capture majestic spirals that appear frozen in time. They look like paintings you could hang on a wall. But that serenity is an illusion caused by the extreme brevity of a human lifespan. Observed over 1 billion years, the universe is a demolition derby. Galaxies are violently active ecosystems that constantly tear each other apart. The universe is a massive construction site. To understand how it was built, we must look past the glowing stars and deconstruct the architecture of a galaxy from the ground up. We start with a foundational physics problem. If you take all normal matter in a galaxy, protons, neutrons, gas, stars, and calculate its total gravity, the pull is too weak to hold the structure together against the expansion of the universe. The visible galaxy should drift apart. In 1939, Horace W. Babcock mapped the Andromeda Galaxy and found that the math was broken. Basic orbital mechanics dictate that stars on the outer edges, far from the heavy center, should move slower. Instead, Babcock saw outer stars whipping around far too fast. The visible mass didn't generate enough gravity to keep them from flying off into space. There had to be an enormous amount of unseen mass, providing the extra gravity to glue the structure together. This is dark matter, a massive, invisible halo that provides a gravitational bowl for normal gas to fall into and eventually form stars. The evidence for this invisible anchor lies in the wreckage of the bullet cluster. During the collision, vast clouds of hot gas slammed together, stopping in the middle. But the mapped gravity kept going. The dark matter passed straight through like a ghost. Dark matter makes up 80% of a galaxy's mass. While supernovae blow normal gas around chaotically, the dark matter remains completely unfazed. Without this indifferent, unmoving foundation holding everything in place, internal stellar explosions would tear the galaxy apart. The stability required for stars to form and for life to evolve relies entirely on an invisible scaffold we can't even touch. This growth engine is cataclysmic. When galaxies fall toward each other, gravitational tides rip them apart. In colliding systems like the antenna galaxies, gravity squeezes the internal gas to trigger the birth of millions of new stars, while flinging long, chaotic streams of older stars completely out into space. Simulations run by the University of Oxford map a multi-phase timeline for these events. When two spiral galaxies meet, they often sideswipe each other on the first pass. Their momentum carries them through the initial crash, causing them to swing far apart like a pendulum before gravity reels them back in for a final coalescence. During this temporary separation phase, the galaxies settle down, the star formation slows, and they can look deceptively normal. If astronomers capture a snapshot during this exact window, they miss the collision entirely, meaning we are likely undercounting active mergers hiding in plain sight. The angle of impact dictates the entire timeline. A sideswipe leaves time for multiple bursts of star formation, separated by a quiet pause. But a direct, head-on radial merger happens fast. There is no separation phase. The galaxies slam together and instantly obliterate their delicate spiral structures. These collisions aren't just destructive endpoints. If the colliding galaxies bring enough raw gas into the wreckage, the collision acts as an engine of rebirth. As the chaos cools, leftover gas spins up and settles into a brand new spiral disk. A galaxy cannot grow indefinitely. If gravity and mergers were the only forces at play, every bit of gas in the universe would have collapsed into stars billions of years ago. Star formation is surprisingly inefficient because something pushes back against gravity and shuts the factory down. We recently caught this kill switch in action. When the James Webb Space Telescope looked into the early universe, astronomers found galaxies that appeared impossibly massive for their young age. These cosmic bodybuilders seem to be assembling stellar mass so fast that they threaten to break our standard models of cosmology. A closer analysis of the light spectrum revealed that this brightness came from rapidly feeding supermassive black holes rather than dense star clusters. As gas swirls into a black hole's accretion disk, friction causes it to glow brighter than millions of stars combined. These young galaxies were just holding bright flashlights that blinded our instruments and inflated our mass estimates. These active black holes act as a galactic kill switch. To form a star, you need cold, dense gas. But as the supermassive black hole feeds, it launches immense jets of energy and radiation outward at nearly the speed of light. It acts as a thermostat, regulating the entire galaxy. The radiation heats the massive halo of diffuse gas surrounding the galaxy. Because the gas is kept hot, the atoms move too fast to condense and collapse. The black hole essentially points a giant blowtorch at the galaxy's food supply, preventing it from cooling down enough to rain back into the disk. By making the fuel inedible, the black hole starves the galaxy. Star formation shuts down. As the short-lived blue stars burn out, all that remains are the ancient, glowing red ones. The party ends, leaving behind a red, dead fossil. To study these mechanics, we naturally look at our own home. We rely on the Copernican principle, the assumption that the Milky Way is a standard template for how a galaxy operates. This scatterplot visualizes the Stanford Saga survey, comparing the Milky Way to 101 similar galaxies. We are a bizarre outlier. Those other 101 systems have satellite galaxies actively forming stars. But the Milky Way's dwarf satellites are completely quenched. We live in a cosmic retirement community. For reasons we are still mapping out, the Milky Way acts as a highly efficient bully, stripping the raw gas away from our smaller neighbors and leaving them dead in the water. That anomaly might be the reason we are here to observe it. If our galaxy were as violently active as the rest of the universe, with constant collisions and rampant deadly supernovae, the resulting chaos could easily sterilize a developing solar system. Our quiet, unusual neighborhood might be the exact requirement for life on Earth to survive long enough to look up. Picture the solar system. Odds are your brain immediately goes to that classic science fair project we all had to build in the 4th grade. You know the one. Painted styrofoam balls, held perfectly in place by rigid wires. Those wires lock everything into predictable lanes, leading us to assume this is how planets naturally behave. We look at the big gas giants circling on the outside and the rocky planets near the sun, assuming this arrangement is a permanent rule of physics. Look closer at the history of our system, and that tidy clockwork vanishes. Our current arrangement is the wreckage left behind after a violent, chaotic cosmic crime scene. For centuries, we assumed our neighborhood was the standard template for the universe. Then came 1995, when astronomers peered through telescopes and confirmed the first exoplanets orbiting sun-like stars. They expected to find clones of our own system. They found chaos. Massive gas giants, worlds the size of Jupiter, orbit closer to their stars than Mercury is to our sun. These behemoths barrel inward on wild elliptical tracks, scattering smaller planets like billiard balls. These discoveries forced a complete rewrite of the rules. Planetary systems aren't collections of fixed tracks. They are dynamic arenas where worlds drift, migrate, and swap positions over millions of years. If the rest of the universe behaves like a chaotic billiards table, our own solar system must have experienced its own era of severe planetary migration. We just have to retro-engineer the evidence. 4.5 billion years ago, our solar system was a massive, cold cloud of drifting gas and dust. It would have stayed that way forever, except a massive star detonated nearby. That supernova sent a shockwave cascading through space, triggering our cloud to compress, spin, and collapse. In the center, gravity squeezed material together until it formed the proto-sun. But this young star was temperamental. It entered a volatile adolescent phase called the T-Tauri stage, blasting radiation and powerful solar winds outward. This created a 10 million-year countdown, as the star actively blew its own planet-building materials out into deep space. The intense heat from the young sun created a boundary about 5 times the distance from the Earth to the sun, a zone astronomers called the frost line. Inside this line, the sun's heat vaporized water and other ices. The only materials capable of clumping together as solids were rare trace elements, silicates, and iron. Building a planet here was like trying to build a castle with only a few handfuls of sand. Outside the line, it was cold enough for water and methane to freeze. Ice is abundant in the universe. Out here, planetary cores could grow fast and massive, so massive that their gravity pulled in hydrogen from the nebula before the solar winds blew it all away. This strict temperature gradient sorted the planets at birth. Those forming close to the fire became tiny rocks, while those in the cold grew into kings. Jupiter was the first to take advantage of that deep freeze. Sitting in the sweet spot just past the frost line, it gorged itself on ice and gas, ballooning to 320 times the mass of Earth. It very quickly became the dominant gravitational force in the entire system. As Jupiter plowed through the thick soup of remaining nebula gas, the friction created intense drag. Constantly losing momentum, this massive gravity well began to spiral inward, directly toward the sun. This inward migration acted like a wrecking ball. Jupiter plowed directly through the inner solar system, sweeping away the dust and gas that Mars needed to grow. Jupiter would have eventually fallen completely into the sun if not for Saturn. Saturn formed slightly later and migrated inward as well. As it caught up, the two giants began to pull on each other, locking into a gravitational resonance that stabilized their orbits and reversed their course. By the time Jupiter retreated, it had swept the inner orbital lanes nearly clean. Mars was left to form in a depleted zone, with almost no raw materials to pull from, leaving it as a stunted fraction of its neighbors. As Jupiter and Saturn retreated, they eventually drifted into a new resonance. For every orbit Saturn completed, Jupiter completed exactly 2. Every time they lined up, they gave each other a massive gravitational shove, pumping huge amounts of orbital energy into the system. The smaller ice giants paid the price for this instability. The resulting gravitational chaos acted like a giant slingshot, hurling Uranus and Neptune violently outward into the darkness. When Neptune was evicted, it crashed directly into the ancient Kuiper Belt, a ring of trillions of icy comets. The collisions scattered this debris everywhere. Millions of icy rocks were thrown inward towards the sun, mercilessly pummeling the rocky inner planets in an event called the Late Heavy Bombardment. Earth should have been a dry, hot rock, but those violent impacts were a cosmic special delivery. The comets that smashed into our planet melted over millions of years, filling the basins that became our oceans. Once the bombardment stopped and the crusts cooled, the inner solar system held a rare sight. 4 billion years ago, 3 distinct blue ocean worlds orbited our sun simultaneously. But Mars was a victim of Jupiter's hunger. Because it was so small, its internal core cooled down and solidified rapidly. The planetary magnetic shield switched off. Without that shield, the constant stream of the solar wind physically stripped away the Martian atmosphere, letting its water evaporate into the freezing vacuum of space. Venus faced the opposite problem. It had shallow oceans for nearly 2 billion years, but as our aging sun slowly grew hotter, Venus crossed a critical tipping point. The rising temperatures evaporated its oceans, filling the atmosphere with steam that trapped more heat, creating a runaway greenhouse effect that proceeded to boil the planet alive. Mercury never even had a chance. The leading theory suggests it was once a much larger planet until a chaotic collision with another world literally ripped it apart, blasting its outer rocky mantle into space and leaving behind nothing but a dense, scorched iron core. Earth's habitability is a fragile achievement. We are simply the sole survivor of a cosmic elimination game, massive enough to keep our core hot and our shield up, and distant enough from the fire to keep our oceans liquid. We look up at the night sky and feel a sense of permanence, but the quiet, orderly system we see today is merely a temporary pause in a violent, ongoing timeline. The sun is still evolving. Driven by the constant nuclear fusion in its core, it is slowly turning up the thermostat. It is 10% brighter today than when the dinosaurs lived. As the sun continues to brighten over the next billion years, Earth will eventually be pushed out of the habitable zone. Our oceans will boil away, and we will share the exact same fate as Venus. We happen to exist right now, at the exact right moment to witness a fleeting window of cosmic stability. Planetary balance is incredibly fragile, and our blue planet is a temporary oasis. When we look up at the moon, we see a symbol of calm and consistency. But if we strip away that silver exterior, its origin story reads like a forensic investigation into planetary annihilation and vaporized rock. For 40 years, the reigning explanation was the Big Whack. Around 4.5 billion years ago, a Mars-sized planet named Theia drifted out of its stable orbit and struck the proto-Earth with a glancing blow. This specific impact angle answered 3 major physical constraints. It provided the massive energy needed to give the Earth its fast rotation. It allowed Theia's heavy iron core to sink and merge with Earth's, explaining why the moon has almost no iron. And the heat of the collision boiled off the water, leaving the moon bone dry. Because this physics-based model worked so elegantly, it became the industry standard for decades, appearing in every undergraduate textbook as the definitive account of our origin. That consensus broke when we began looking at isotopic signatures. Every planet has a unique chemical zip code based on where it formed in the solar nebula. By measuring the ratios of isotopes like oxygen or tungsten, we can tell if a rock came from Mars, an asteroid, or Earth with incredible precision. This creates a crisis for the Big Whack. If the moon is made mostly of Theia's debris, as the model predicts, it must carry Theia's distinct alien chemical signature. But the evidence didn't add up. When geochemists analyzed the pristine samples brought back by Apollo astronauts, they found something impossible. Modern mass spectrometers prove that the moon's isotopes are identical to Earth's, to within a few parts per million. Chemically, the moon is Earth's identical twin, not Theia's child. This is the mixing problem. Standard physics says a debris disk cools and clumps together too fast to blend 2 different planets into a perfectly uniform soup. The old collision model cannot explain an identical twin, meaning the entire theory requires a more extreme starting point. One solution suggests the moon wasn't the result of a single lucky hit, but a sequence of smaller ones. This multiple impact hypothesis proposes that Earth was essentially mugged by 20 different moonlets over millions of years. In this model, each small impact creates its own debris disk and its own mini-moon. Over time, these moonlets migrate outward, catch up to one another, and merge to form the single large body we see today. This solves the chemical crisis through statistics. By absorbing 20 different rocks from across the solar system, the final moon averages out its chemical flavor until it matches the overall flavor of the Earth. But there is another theory, one that requires an impact so energetic it completely dismantled the solid structure of the Earth. This is the synestia. An impact on a 2-hour spinning Earth vaporizes and inflates it into a massive 4,000-degree glowing bagel of rock vapor. Inside this surfaceless cloud, Earth and Theia material are churned together for a century, perfectly mixing into a single homogeneous soup. As the synestia cools, magma rain begins to condense. Most of it falls inward to rebuild the Earth, but some clumps together in the outer edges to form the moon. The moon is essentially a droplet of Earth vapor that condensed and got away. If these two worlds were fused so violently, we have to look past the sky and into the deep Earth to find where the rest of Theia ended up. Newer simulations suggest that large, dense chunks of Theia's mantle didn't vaporize. Instead, they plunged through Earth's magma ocean and settled there, resting right on top of our core. We see these today as large, low shear velocity provinces, massive, continent-sized blobs of rock that slow down seismic waves. Earth is a chimera. We're standing on the physical remains of an alien planet that continues to influence our volcanoes and magnetic field 4.5 billion years later. The cooling of this global magma ocean was the critical turning point for life. High-pressure chemistry at the base of the ocean oxidized the mantle, creating rust, and left the crust lubricated with enough water to break into mobile plates. This kick-started plate tectonics, the engine that recycles carbon and regulates our planetary temperature. We can see the alternative on Mars. Its magma ocean froze into a stagnant lid, a single immobile crust. Without tectonics to recycle its atmosphere, Mars became a frozen desert with dead volcanoes. But even with tectonics, Earth faced another threat. Our young sun was a violent, radioactive teenager, blasting the solar system with flares intense enough to sandblast an atmosphere away. We desperately needed a strong magnetic shield. We likely powered that shield through a process called magnesium snow. The violence of our formation forced light magnesium into the core, but as the core cooled, it became less soluble and snowed upward into the mantle. This rising material stirred the liquid iron, powering a magnetic dynamo billions of years before our solid inner core ever appeared. At that time, the moon was 10 times closer to Earth than it is today, and because it was young and hot, it possessed its own small molten core and its own magnetic field. Because of that proximity, the magnetic fields of the Earth and the moon coupled together. They merged to form a single, massive protective barrier that draped over both worlds. This combined double shield provided the strength needed to deflect the sun's fierce solar wind, preventing Earth's atmosphere from being stripped into deep space. The moon functions as a detached, vital organ of the Earth system. That chaotic violence, the vaporizing of two planets and the scrambling of their chemistry, was the necessary price for our habitability. Without it, we wouldn't have the spin, the chemistry, or the shield that makes our world possible.